Hello, I'm Steve Johnson. Welcome to Digital Works TV. Our special guest today is Dr. Dale Thomas, UAH Eminent Scholar of Systems Engineering. That's UAH, University of Alabama in Huntsville. Am I correct? You're a professor and you
Correct.
teach and you also do some other things. Am I correct? You have worked at NASA also?
Yes, I have, Steve. I've actually worked with NASA for 32 years.
Okay.
At Marshall Space Flight Center and at Johnson Space Center in Texas. And then I retired in 2015, not 1915. And
Well, you look good.
thank you. And so in the last 10 years, I've been out at UAH.
Okay. And right now, and I'm going to say this, and you're probably going to correct me, but you are working on a project with students involved for NASA to develop nuclear propulsion, the kind of thing we would need if we want to have humans go to Mars way faster than we are capable of doing otherwise. Is that?
That is correct.
Okay. Because we can't carry enough gasoline, but we can carry enough fuel to run nuclear propulsion.
Yeah. So it's really interesting. People think about, going to the beach and you think about it in terms of miles, okay?
Yeah.
But when you're thinking about going to the moon or Mars or Jupiter, other destinations in the solar system, it's best to think about it in terms of velocity, okay, which is, miles per hour.
Yeah.
We typically talk in kilometers per second.
Yeah.
And that's because the different bodies orbit the sun at different velocities. Yeah. And Mars, even though it takes longer than a year to circle the sun, okay, so intuitively you might think it's going slower. Actually, it's going quite a bit faster than the Earth. It's just got a much bigger distance to cover in an orbit. And so if we're wanting to go, say, from the Earth to Mars, we have to get going a lot faster. Yeah. And as we get going faster, the laws of physics, we will get further out from the sun, and that is something that was discovered a couple of centuries back. You work it just right so that you match your velocity at the right time to your destination, and you time your launch so that the planet's going to be where you want it when you get there.
Yeah, so it'll be the short, because you want to take the shortest amount of time to get the human beings from Earth to another planet.
But it's all about matching velocity, and this is something that Kepler figured out. Like I said, I think about 300 years ago. Yeah, he made a contribution or two along the way. Yeah. But yeah, Kepler, Newton, all those folks. Now the reason I'm stressing velocity is chemical engines. When they blow, when any rocket engine blows the hot gas out the nozzle, you're basically pushing the rocket in the other direction.
Yeah.
Okay. Just simple conservation of momentum.
Reaction.
Yeah. If I push you, you push back. That's all. That's the way a rocket engine works. It's called thrust. All right. And the speed at which the gas comes out of that nozzle, okay, is a function of several variables, but very principally temperature and molecular weight of the atoms coming out. So when you're combusting propellants, the molecules that result from that combustion and the temperature they come out, they dictate how much thrust you get out of that engine.
Yeah.
Well, with nuclear propulsion, you don't have to use oxygen to combust. You're just removing heat from the reactor. So you can run a very lightweight gas through that engine as your propellant. And because the molecules are so much lighter, you're getting much more specific impulse, or if you will, efficiency out of that engine.
You could carry a lot more fuel with you.
And it lets you go a lot faster.
Yeah, and am I correct, when in the Apollo mission, when we went to the moon, we were going, 25,000 miles
that's about
an hour
what it is,
something like that?
Like I said, I tend to think in kilometers per second, but I think that's about
something
it.
like that.
It's in the ballpark.
Okay, to go to Mars, I mean, if we went to Mars at 25,000 miles an hour, people would be much older by the time
Well, and that's why I was talking about, you got to think about it in terms of velocity. You can't get to Mars at 25,000 miles an hour. You can only get to the moon, which, by the way, the moon in terms of distance is not that far from Earth, right?
Yeah, all the
But in terms of velocity, you're halfway to Mars.
Yeah.
So, yeah.
Okay. So that makes the ongoing projects and the talk, and I think it sometimes gets lost that the moon could be a way station.
An excellent way station.
Way station. Well, first of all, I'm getting ready to astound you. The delta V, or the thrust needed to leave the moon to go to Mars, is a whole lot less than the thrust needed to leave the Earth.
Exactly.
I feel pretty smart now.
You got it.
We should stop.
Hey, well,
Interview over.
the reason I stress that is because it's not intuitive. Like I said, we all think from driving our cars, we think in terms of distance.
Yeah, but
and how long it takes us to cover the distance. And if we go faster, we just get there in a shorter amount of time, but we're still covering the same distance.
well, you're covering a distance. Not only are you covering a distance, but the distance. There's a closest point, but the distance is getting farther the longer you travel. Is that correct? Or
Well,
you could launch so it's getting closer. I mean,
yeah,
because Mars is going like that.
But you've got to match that velocity.
Okay.
Is
So
the
how
thing.
fast? So let's put it in terms of speed. How fast do you need to be able to go to get human beings from Earth to Mars in a reasonable amount of time? In a reasonable amount of time, I keep hearing 9 months. Seems
So-
like,
So to get to Mars on what we call, a Hohmann transfer, which is what I would call the most efficient path
Yeah.
to get to Mars in terms of propellant. It's making the orbits line up, if you will.
Yeah.
Okay. That is about a 9-month transfer. Okay. And what happens? You leave the Earth just right. You get up to your high velocity, and you time it such that right about the time you're getting out to Mars orbit, Mars is getting there too, and its gravity captures you, and you're there. If you want to get to Mars faster, okay, you have to go faster than, go to a higher delta V than you would need to get to Mars. Ideally, like get on a delta V that would take you out to the asteroid belt or something.
And by delta V, we mean the
faster. You're just going
faster. And the power. There's also the power required to achieve that.
Well, yeah, you just need more propellant, or you need, the gas coming out of the engine at higher velocity.
Okay, just so I'll understand, if we were to get all our material, all our equipment to the moon, and we went from the moon to Mars, does that shorten our time?
Not that much.
Okay.
Now, that said, what it does enable you to do is, like you said, you can overshoot on your velocity, and then when you start getting close to your destination, when Mars is coming up, then, if you will, you thrust in the other direction, if you will, tap the brakes to slow down so that Mars can capture you. And with trajectories have been run that, let you do, approximately a 2.5 month journey instead of a 9-month journey. I mean, you can get there a lot faster.
Okay, so the moon, get some time there, and it is, everything. It costs money to get stuff from here to the moon, and it costs money to get anywhere. When you're leaving the Earth, it costs money.
We call that Earth's gravity well, because Earth, has a big gravity push, plus the atmosphere. Getting up into orbit is not easy, as von Braun and all the pioneers figured out. And then once you get out of the atmosphere, then you've got to get on up to Mars, on up to the moon. But in terms of velocity, you're halfway to Mars when you get into lunar orbit.
You're working on a nuclear propulsion project.
Right.
Okay.
We sort of got a feel there.
Nuclear allows you. Well, first of all, if you were to take what we fuel our rockets with now, that would require carrying a whole lot of fuel a long way.
Yeah. So as a matter of fact, you can't make an Apollo-style mission to Mars work, because going back to the amount of thrust and velocity and everything you can get out of those engines, you can't carry enough fuel with you for the round
just not
trip.
Efficient enough.
Not efficient enough. So if you look at, for example, SpaceX has a Mars architecture where they send vehicles ahead of time, and they start generating the propellant on the Mars surface for the trip back
Yeah.
home. So it's like tanking up your car
Yeah.
at the beach to drive back home after you've driven to the beach. So you can make chemical propulsion work in that scenario.
Yeah.
Okay, but you just don't have enough power to make it work for the round trip. Now, with nuclear, because it's so much more efficient, you can do an Apollo-style mission where you go there, do your mission, and come back home without refueling.
Okay, so that's what you're working on. Well, let me
That's
ask
what
you
we're
this.
working
I
on.
mean, SpaceX has this idea, but right now, unless you put something on Mars to do some work for you, and it wouldn't have people with it, I don't think. But it
Yeah.
could. I mean, that's up to whoever, and it's a few years down the road. Nuclear or something similar is almost a requirement to go to Mars. Am I right?
Yeah, as a matter of fact, when NASA, back in the Constellation programs, was working on the Mars architecture,
Yeah.
okay, what we were going to do, nuclear was the, if you will, preferred baseline
Yeah.
for the
Okay.
propulsion for that reason.
Okay.
Because otherwise you've got to, there are a couple of ways. If you don't put equipment on the surface to generate the propellants, then what you've got to do is launch a bunch of rockets and put the propellant depot in Mars orbit
Yeah.
that you can tank up
So
from
it
to
gets,
come back
it
home.
gets, trying to use what we use now, conventional rocket fuel, it requires, it seems to me, a whole lot more trouble and a whole lot more expense. Other than, you know, but if you could get nuclear propulsion to work like you want it to, that's the way to do it.
It is the simplest, yes.
Okay. All right.
And by the way, a nuclear rocket engine is simpler than a chemical rocket
Oh,
engine.
yeah. So, since engineering is what we are here, let's talk about that as an engineering problem.
Sure.
And so you're an engineer by trade.
I
Am I
am.
correct?
Yep.
So,
I am a degreed geek.
okay, degreed geek. I know several people just like you. I am not, but it is fascinating stuff. But let's talk about this as an engineering
Okay.
problem. What's the toughest part of figuring this out? I mean, is it just a matter of there's some slide rules on the wall behind you? Could figure it out with those. We don't do that anymore. We use computers.
Well, so interesting you should ask that question. So I'll answer it, and then if you
No.
don't think I'm answering the question you ask, I'll come back. But the answer I'll give you is that the hard part is actually building and realizing the machinery.
Yeah.
Okay, and by that I'm not talking not software. I'm talking about the entire system. The example I'll give you is the physics and the concepts for going to the moon were around in the early 1900s.
Well,
You know.
and maybe people don't know, but Von Braun had a plan that he actually presented. Am I correct in 72 or early 70s, where he went and presented his idea for here's how we would go to Mars.
Oh, yeah, as a matter of fact, that's when he, after Apollo
Yeah.
was going, it was still going on, you know, he was pulled up to headquarters to start developing the Mars architecture. So, yeah, the mechanics of it are well known. There are various concepts that are well defined and have been around a long time. And going back to Apollo, that had been done, you know, 50, 75 years before Apollo. It's actually building the rockets, you know, building the spacecraft, you know, the life of the spacesuits, you know, all that stuff. The lunar lander was an incredible engineering challenge, okay, to get it lightweight enough and everything.
Yeah.
So it's, there was a saying when I was at NASA from, you know, the veterans, and it was the devil's in the details. And yeah, the big picture, we know how to get to
You know how to get
Mars.
here, just
Yeah, it's just
having a race car that will go the distance on the amount of fuel allotted.
exactly.
That's,
Yeah,
that's
just getting all the pieces built
So-
and working together.
So, as an engineer, and engineers in general who think about these things, so you look at, okay, here's what we want to do. Well, how can we do that? How can we do that in a reasonable amount of time for the most reasonable cost available, and be able to not only go but come back and keep
Yeah.
our astronauts alive, which is a whole nother thing.
I'm glad you brought that up, and I'm sorry to interrupt because I know you're in the middle of a question, but
No,
I've got more gray hair than you do, so I'll do that. But one of the biggest challenges of a human mission to Mars is keeping the astronauts alive for that amount of time in the deep space environment, where you're out there, you're fielding cosmic rays and all that. And, one bad solar storm and you've lost your crew.
Well, and a good friend of mine, and I believe a friend of yours, Mike Rudolphi, Rudy to his friends who passed away, he said it could be that the biggest challenge of all, not the propulsion system, not the rocket, but getting the people to and from, not only healthy because of the things you mentioned like cosmic rays, but psychologically healthy. That how do you do that? He said that may make the trip impossible. And I know that we don't really think of it that way. Yeah, sure, we can go.
No, I'm with you. The Mike Griffin, I'm sure you remember him, and I wish I could remember the exact setting, but I remember the discussion real well where he said, we will only be ready to go to Mars when we launch a crew to the International Space Station and they stay there for 9 months with no, spare parts or anything coming from Earth, and then we send them to the lunar surface for, the year and a half, whatever the nominal service time on Mars would be, and then we bring them back to the station for 9 more months, and then we bring them home, and we've done all that without them needing anything else from Earth.
So there's I guess this would be the soft engineering, making the figuring out how to get the people to do all the things, and then it begs the question of who gets to go as a crew. Do you need two sets of two couples that are all doctors? Because and if a wrench breaks, you've got to be able to 3D print on your spacecraft, and these are all things that are that practice and thinking about. Those are all things that have to be thought about.
Well, the good news is some of the technologies are coming along at exactly the right time.
Yeah.
I mean, we couldn't have lined things up any better. For example, you've got additive manufacturing, and we actually have some experiments.
Which I call 3D printing.
Okay, 3D printing.
It is additive manufacturing.
But we have some of those experiments, and I mean, we were even flying some of those before I left NASA in 2015 on the International Space Station. We're learning how to print stuff.
But did they not put a 3D printer on the station? I know that was a project. So they can 3D print on the station.
Well, so I don't know exactly where the state of the art is now, but like I said,
that was the goal, to put one.
Yeah.
Because you're going to have to. There's the medical problems for the astronauts, and then there's the parts problems.
Yeah.
You can't. It's hard enough if we have a station on the moon. The guy's got appendicitis.
You got it.
Well, fix it, because the doctor won't be there in time.
Yeah. So so that technology is coming along, and artificial intelligence, machine learning is coming along to give you a lot more power, on your computing system. And I hesitate to make the analogy, but hopefully you'll understand where I'm going with it. HAL on 2001,
2001.
capable of doing a lot of things, but where HAL struggled was in the edge case, that really wasn't nominal. All right. And, but, those are very occasional. Ideally, that's why they're edge cases. And so you can't ever take ground support totally away. But my point is, we've got some technologies coming along that we really need to address some of the problems you're talking about. The logistics chain, mental health, and, quantum technologies coming along that may enable faster than light communication. Now, I've heard other people who are learned on this subject say, no, it really won't be able to do that. I've heard others say it will.
When you start talking, if you want to get a headache, and you probably know this, and you're a professor, start reading about quantum mechanics. In fact, I suggest you do so.
Well, I'll do.
It will give you a headache. It's like,
Yeah.
and the fact that some people think that
Yeah.
way, it just drives me.
Well, we were talking about Einstein earlier, and Einstein hated quantum mechanics.
Yeah.
But he recognized it actually does describe the phenomena that we see. So he begrudgingly used it, even if he didn't like it.
But it really is an interesting subject. But
Mm-hmm.
but we're talking right now something that is more an engineering subject.
Yeah.
It's where it's seeing the challenges and coming up with the answers.
Mm-hmm.
Like you said, the mechanics of going to Mars, we've known that. We
Yeah.
know what we have to do.
Yeah, Kepler solved that.
And then von Braun had a whole architecture for doing it. But
And by the way, that's back in the 60s.
Yeah,
We had a nuclear rocket engine program called the NERVA
Yeah.
that was being developed in large part for the Mars program.
and like many things, a long time ago, back in the sometime in the 50s, my dad worked at Oak Ridge, Tennessee, when they were working on
Okay.
nuclear airplanes. And I believe that's right.
They,
So that was
they
that
did
was-
play around with that a
Yeah,
little
that
bit.
was
yeah.
that was. He went back to North Carolina State after that. So
Good call.
We've known the technical challenges.
Right.
But for engineers, how do you guys look at this? Is like, I know everybody hasn't seen the movie The Martian, but if you want to see something hopeful that will make you feel good about human initiative and human ingenuity, that is a great movie. Where you get a problem, you do the science, fix that, and go to the next problem.
Yeah.
So for engineers, when you look at going to Mars now, and all the other engineers who are thinking about this, or thinking about any kind of probe or mission to another planet, what is the thing that you think, that's what we've got to do? That's the one we have to solve.
So that's actually a very insightful question, Steve. And what you always try to do is say, all right, if we're going to do this, what is the first problem we got to solve? Maybe what's the toughest problem we got to solve? There's a piece of advice, I think it was from Eberhard Directing to Aerospace Corporation, one of the founders, who said, do the hard part first, okay? So you look at all the challenges, like you said, all the stuff you got to do, and you tackle the hardest ones first. Like, for example, going back to Apollo, they knew they needed some bigger rocket engines, that to just cluster a gazillion rocket engines the way the Russians were doing was not a good approach.
Yeah.
So, they focused on developing the F-1. They also knew that they needed to develop the technology to do in-space rendezvous.
Yeah.
Okay. So they said, okay, how do we do that? Let's come up with this program called Gemini, figure it out, show that we know how to do it. So you just, you knock those big problems down. Like, for example, one of the big ones we'll have to solve and go into Mars is a better closure of the water loop. Like, for example, on the International Space Station now, they recapture water out of the atmosphere.
I have, at Marshall Space Flight Center, when they were developing that project, I was given a bottle of the water.
Yeah.
It tasted faintly of iodine. But it was basically recaptured waste.
Yeah. So the water loop on ISS now is currently in the low 90s closed. And they've been working on that
So when you're in low 90s, they're
Oh, low-
retrieving about 90% of the
Thereabouts, yeah.
available.
Yeah. And so the way they make up the difference, okay, is by carrying water up from Earth periodically on the resupply flights. Now, the good news is you're not having to carry up all the water you need, only about a tenth of what you need.
Yeah.
Well, I think you can see where I'm going
No, I
with
see where you're
this.
going. That it's going to have to be 100% to go to spend 9 months and then have the ability to extract whatever water's on Mars before you can come back.
Yeah. Or, in engineering, we know we won't get to 100%.
Okay, yeah.
Okay? But we sit down and play with our tolerances and say, all right, well, if we want to, be able to get there and back with, with water to spare,
Yeah.
okay? Our system, we can carry this much spare water, and our system has to be 99.3%
Okay, so we
effective.
have to get close
So
to-
it sets us a goal, and then we, turn around and say, all right, can we achieve that. And, then we go do a lot of work, maybe build mock-ups in the lab, modeling and analysis, testing, and, then after all that, we've come and said, we can get to 98.5%. Okay, can we carry enough spare water, to do that?
And while you'd say, well, 98.5%, but if you 98.5% and you stretch that over 9 months, that comes out to several gallons of water.
Quite a few. So that's why, it's a very iterative process. The technologies are all coupled together. And so, like, for example, let's say we did that and, that was just the brick wall and you ended up having to carry a lot more water than you were figuring. Now you've got to go back and, perhaps re-engineer the size of your spacecraft so it has a bigger tank of water to carry.
Wow. And then that basically, that kind of problem holds true, I would imagine, for every single system that isn't just a piece of metal.
Yeah, pretty much.
So,
and that's, that is the challenge that, NASA folks love. Okay. And I'll just say aerospace in general.
No, I mean, and we the Apollo program, we knew what was needed, but they, I mean, talking to the guys, and I was fortunate enough to talk to several of the guys who worked on the Saturn V. They didn't even know some of the problems they had until they had launched 8 times.
Yeah,
and it's so. But with the Mars mission, you can't figure out, we should have thought of that.
No.
When the spacecraft is 4 months down the road and there's no like stop and coming back, it doesn't work that way.
And that's one reason why I think a robust scientific exploration campaign of Mars is warranted. So I've always been an advocate of let's put a base on the moon, think crawl, walk, run. We'll discover some of those problems on the moon, which is a whole lot easier to get to and fro. We used to unfortunately call problems that we would encounter at NASA, we'd say, well, it was a lack of imagination. We just didn't see that problem coming. And, putting a base on the moon and, sustaining it and working there for a few years, we'll discover some of those problems we lack the imagination to think of.
It's so hard, though.
Yeah, that's what makes it fun.
Not to overcome the technical challenges, because that has been a fairly steady progression for space flight and many other things. But to have the ability to be patient and know it's going to take time. I mean, think about it. We already were building rockets and missiles and things when Kennedy made the promise we'll go to the moon within the decade, which was 9 years away when he made that speech. But it was a close thing going within the decade. I mean, they had to overcome things, and they didn't understand problems in some cases.
And, like, for example, the Apollo 1 pad fire, that took the lives of Grissom, White, and Chaffee. That was another failure of imagination. And, had we had the imagination to not have to go through that, in addition to preserving those 3 men's lives, we would have gotten to the moon quicker.
Okay. All right, let's talk about how systems engineering, you're an eminent scholar, so you should be able to talk about how systems engineering fits into this. I mean, systems engineer has kind of got his arms around all the things that go together to make this, but this going to Mars thing, let's just go with the nuclear propulsion. That's the thing you're working on. That's a system that has some pretty, I would say, interesting parts and interesting aspects. And so how does a systems engineer approach that?
So as a system engineer, I start with, the nuclear engine and take the nominal performance parameters of that engine, how much it weighs, how much thrust we think we can get from it, what the specific impulse is. And by the way, specific impulse, that's a measure of efficiency for a rocket engine akin to miles per gallon is for an engine. It just tells you how efficiently you're using the fuel. But you take some of those key parameters and then we design notional stages that, we can parrot other in-space stages. And, so we run simulated missions.
Yeah.
So it's sort of like, okay, if we can get this engine working like this, what can we do with it? And then from those simulations that we've run, then we turn around and say, well, let's tweak this parameter, okay? And
You're leading to my next question.
so, one of the things we did, NASA, was running a lot of pretty intense, analysis on the human mission to Mars.
Yeah.
So at UAH, we started looking at scientific missions to the outer planets.
Yeah.
And so to make it a little more challenging, we said, no, let's not assume SLS. Let's go with a commercial heavy lifter like a ULA Vulcan or a Blue Origin New Glenn, and let's see what we could do with that. So as it turned out, you can get notionally flagship class payloads. By this, I'm talking something like, 2,000 or more kilograms, big spacecraft.
Everybody's going to have to go look at their conversion after this.
Oh, I'm sorry. So about 2 tons, 4,000 pounds, and even higher. Okay. You remember the missions to Jupiter that we've done? You launch them, and 5-6 years later they get to Jupiter, right? Because they have to fly. Our rocket engines aren't good enough to get us there. We have to do these planetary flybys, and steal momentum from the planets.
That isn't a human being thing. That's a payload. No need to rush it. It'll get there.
Yeah.
So, and it's a lot cheaper
to
not have to provide thrust.
Well, not only is it not cheaper, you literally can't get there without it because our rocket engines,
they can't carry enough fuel.
Well, their exhaust is not coming out fast enough to let you accelerate fast enough, So, but with a nuclear thermal propulsion, we can do that. And
you can provide thrust the whole way.
Yeah. Well,
or not. You could provide more thrust longer.
Well, or I'll just say because your exhaust stream is so much lighter, it's coming out a lot faster, and so you're getting a lot more push out of it.
Okay, and remember, and everybody needs to remember, in space, there's no atmospheric resistance.
That's right.
The gravity, there is gravity though, and you talked about using the gravity of other planetary bodies or moons or whatever.
Playing crack the whip
to help direct, so.
But we had to do that because with the chemical propulsion, we couldn't get our spacecraft out there. So anyway, coming up with a nuclear powered stage and a sizable payload, instead of it taking us 6 years to get Jupiter, we get there in 2.5.
Okay.
Because we can just fly a direct trajectory.
Okay. So all right, because that's so. Yeah. That's a good exercise to show what nuclear propulsion does.
Saturn in 5. Okay.
Yeah.
Not 10 or 11, but 5. Okay. In general, you cut your transit time to the outer planets in half.
Okay.
All right. And these are rendezvous missions too, not flybys.
That would be, of course, from Earth to Mars is different from the Moon to Mars.
Oh yeah.
So the Moon to Mars is quicker. So, but you could cut. It's really not even necessarily cutting the time. It is cutting the time, but it's also being able to go.
Right. It's actually both. You're right. To get to Jupiter or Saturn or any of those using chemical propulsion, you have to do those exotic trajectories, and because you're flying all around. Think of it, as getting from here to Atlanta by driving through St. Louis. Okay. It's going to take longer.
Yeah.
All right. As opposed to just driving straight to Atlanta.
Okay. Okay, and one thing I wanted to say as a systems engineer, like when you're developing this rocket, if you want to say, hey, it would work better if this was a little different. Well, in model-based systems engineering, am I correct? If that's a little bit bigger, then what does that mean to that over there and these other parts?
So as a matter of fact, that's exactly what we did, and the conclusion to our study, we ran a lot of cases, and one of the things we were interested in is, okay, what should the design specs, what should we try to design this engine to do?
Yeah.
And we found out sort of the sweet spot we should try to design for is around 15,000 pounds of thrust, okay?
Okay.
That bigger than that, is it's detrimental, and smaller than that, it's detrimental.
Okay, it would require, either extreme would require changes to the basic,
Well, it's just
power
going
plant?
to, it's going to require more propellant
Okay.
to
Oh,
get
okay.
you to where you want to go,
So
if
that's-
you will.
And that would in turn, if you carry more propellant, cause a whole nother raft of problems.
Yeah,
to
well, you
solve.
got to, if you carry more
Yeah.
propellant, bigger tanks,
Yeah.
which weigh more, which means you got to have, more propellant
Yeah,
and bigger.
yeah, it's okay.
It's a feedback loop on itself. But we found that sweet spot, and we've shared those results with NASA. We also published, the results that demonstrated the viability of
Okay.
direct trajectories, what I was talking about earlier, to Jupiter and Saturn using an NTP stage off a commercial heavy lifter. And we published the paper, and about a year later, the Chinese published a similar paper.
Ah, well, of course. Okay, so
But we did it first.
systems engineer, model-based, how does model-based systems engineering fit into this? And you told me once that, Digital Works is about, one of the things we're about is giving students the opportunity to go to a 2-year college, a community college, and become a systems engineering modeler. Somebody that would work with a system, who would work with a systems
Okay.
engineer.
Now, I didn't tell you that. Chris Crumley probably did.
Well, he did.
Okay.
But you told me that your modeling that you're using, you say your modelers are like doctoral students very often.
Yeah, they're all graduate students.
So, I guess I think it's cool that somebody could go to a community college and they wouldn't know as much as a doctoral student, a doctoral candidate in engineering, but they would be able to work on something like a Mars spacecraft.
Oh, that's very possible.
And I mean, that's pretty cool, actually, that you could get into a field and do something like that.
I think it's pretty cool.
So, model-based systems engineering, that's what Digital Works is about.
Yeah.
And that's, you're an eminent scholar in it. So, what would you say, if you were going to say, Steve, I don't know why anybody's doing it any other way. This is the advantage. What would you say?
Well, so I'll say that back in Apollo,
Yeah.
and even during my tenure with NASA, the way the system engineering work got done and the way most engineering got done was, information has to move back and forth.
Yeah.
The kind of stuff I was just talking about on engineering, a run case for us to get, a scientific spacecraft using, all these parameters to Saturn, say.
Yeah.
And
Yeah.
so all that was written and documented in paper, okay? And the neat thing, what model-based lets you do is you've created a model of that. It's much more compact.
And it's digital.
Well, it's all digital.
It's all digital.
But it's, I'll just say it's much more self-consistent. And the point I'm going to go with that is, so when you've got, a document this thick talking about all the assumptions and, the margins and all that kind of stuff, and something like you was talking about earlier where you want to go change this parameter and see what that does. Like we were talking about earlier, that we want to get to 99.5% efficiency, but we can only get to 98.5, okay?
Yeah.
What does that mean? Well, engineers are running what-ifs like that all the time.
Yeah.
And what'll happen is then engineers in different parts of the organization get on different wavelengths, if you will. One's running one case and one's running another, and
No,
they
it's
do
like,
that.
like if a structural guy was building a rocket, big old robust structure, the guy's going to, how much fuel going to carry? Something much smaller, and they've got to make those things come together in what they can actually do.
And the model, I go in and I, in the system engineering model, and I change that efficiency from 99.5 to 98.5. All of a sudden, everything it impacts shows up.
Yeah.
Okay, and
This
it
is
goes
using
from
the
green to
digitally
red.
based model-based systems engineering.
So that's the real power of the model, is you're able to keep everybody on the same page.
Okay, and it also, am I correct, and this might not matter to anybody, but it does allow you to move faster. And one of the things that just drives the know-nothing civilian, which I am one of, why does it take so long to do every time we design a rocket? We've already built rockets. Why does it take so long? Well, it takes so long because everything requires testing and study. Am I right about that?
That's one of the reasons it takes so long.
Okay, money's another. I know that.
Well, no, it sort of goes back to that loop when, something that you're trying doesn't quite work, and you have to adjust it.
Yeah.
Okay. And that because of the coupled nature that we were talking about, it ripples, to 4 or 5 other things. It then have to say, okay, what does that mean to us? So, in this case, we were talking about, well, we've got to haul more water, okay, because we can't, make up enough or reclaim enough, okay? So that means you've got to have a bigger tank, okay? Well, that bigger tank is simply bigger, and it's going, to be heavier, more massive, so the structure supporting the tank has to be stronger, okay? So, and that structure that's heavier is probably more massive, okay, which you can launch the tank empty. It may not be much heavier, but then the structure's heavier. So, lo and behold, I've got to have more propellant to get the heavier rocket or spacecraft up to orbit. It just all feeds back on itself, and that's why it takes so long.
And so the model-based systems engineering, though, the fact that if you change one thing, it shows up. You can see how it affects other things. That's where speed is probably the wrong word, but where some time is saved. Is that?
Yeah, time is saved because, as I said, if I go change a parameter, it's going to set flags or alarms on everything that gets touched. And at least everybody is aware of that and can go look at it. And what would happen in the olden days is if I was making a change, if I was very studious, I would think of all the people who might be impacted by this change, and I would let them know.
Okay.
But, failure of imagination, I might forget one key person I needed to know.
Affect them, but it would.
They keep running open loop, and we discover that disconnect 6 months down the road, and we got to back up and fix the problem.
Okay, so model-based systems engineering that's the cutting edge of doing this. Am I correct?
It's yes, and
I know. I'm oversimplifying everything.
Within a larger context of digital engineering, yes.
So why doesn't every company, and they do kind of, but why doesn't everybody just say, okay, we're going to do it this way because this is the best way to do it? Why? I don't know, and I'm not an engineer, so is there pushback, or is it just getting everybody to think that next kind of thing is hard to do?
Well,
I didn't ask that question very well.
No. I understand what you're asking, and it's there actually has been some research on that. Not as much in model-based system engineering per se, as in the entire thing about like going to Industry 4.0. Okay, for example. So there's quite a bit of research about, okay, when we've got better technology, why aren't we using it? Okay. And as it turns out, a very big part of that is organizational inertia. If I've been a system engineer.
So I've been doing this and it's worked, so let's just keep doing it this way.
Yeah. I mean, I know that, folks say that I can do my job in half the time, but I've got to have something I've got to get done by the end of the week. I don't have time to go learn this new skill that will let me do it in a shorter amount of time.
Okay.
There's an investment required.
No, I get it.
So that's part of it. That's not the whole story, but that's a big part of it. And a big part of it is the legacy. There's a lot of the systems that are out there working were developed using traditional system engineering methods, and it just does not make a lot of sense to go reinvent the wheel there just to be model based.
Here's the deal. We went to the moon using slide rules with big, you look at the video now, and it looks like we shot 100 years ago, of rooms full of guys with draft boards drawing parts and systems on a
Yep.
piece of paper.
Mhm.
That's how we went to the moon. We don't do that anymore. So
No.
we moved to the next step,
Mhm.
and my feeling is that model-based systems engineering, and this is when I hear that step is coming.
Oh,
You know,
yeah,
so
absolutely.
that is a step, and it's a question for whoever
Mhm.
to go ahead and say, you know what, we should be at the point of the spear on this, and
Oh,
not back on the stick.
well, that's why, you know,
Yeah.
when I joined UAH, in my second year
Yeah.
there, uh, so in my first year there, I went around and I met with folks in Cummings Research Park, Redstone Arsenal, Marshall Space Flight Center, and the message was loud and clear. You know, we need our students trained in MBSE, so I developed the course in it out at
Yeah.
UAH and started teaching it. And you know, it just takes time. You know, just because you've got a better tool doesn't mean you flip a switch and it's
Okay,
used instantaneously.
are you saying there that it's coming?
Oh, absolutely.
Okay,
Yeah,
it's
but
just,
so when I was in college, okay, 45 years ago, all right, I took drafting. I mean, I learned to draw on a
Yeah.
drafting table, okay? And one of my peers in class, he was working nights at a small company called Intergraph,
yeah.
okay, developing this new
Oh,
thing.
I know where where we're headed with this.
Yeah. And so I would actually come out with him some nights and just play on the machine because I
Yeah.
thought it was so cool to do on this machine
What you were doing.
what
by
I
hand.
had learned to do
Yeah.
by hand. And then, you know, fast forward 10 years, 15 years, 20, and, you know, the tools get really good, and I'm not sure at what
Yeah.
point, but manual drafting is not taught
Yeah.
in schooling board because there's no
Yeah.
more demand for it. But I will say, when I, you know, first joined NASA then in '83, there were still drafting tables out
well,
there.
yeah, and there were, and it's the reason in a paperless society, everybody has a whole bunch of paper. Because it's
Yeah.
hard to let go of the way,
And not
the
just
way you did-
hard, it doesn't make sense 100% of the
Yeah.
cases.
yeah,
We did a study, I'll get a little off track here, where we actually found out that we don't think we'll ever get rid of textual requirements, okay? Because sometimes you need ambiguity, and when you start putting a drawing down,
yeah,
it's hard, you know, to say, well, this can be this range, or, you know, it's hard to be ambiguous. Not that you can't do it, but it's easier in the spoken word.
okay.
And if you want precision, that's easier in a diagram or a drawing.
Yeah.
So, but sometimes you want to be a little vague in what you're asking for because you want to allow some freedom in the
Well,
design.
and isn't that one of the advantages of model-based systems engineering? Because, and I've heard this from students learning to be modelers, that there are many ways to come at something. And
Oh,
that's
yeah.
one of the things they love about the discipline, that it allows for a variety of ideas
Absolutely.
to arrive at the best solution.
Yeah, it's a little more obvious, if you
Yeah.
will, because like I was talking about earlier, now instead of this whole stack of
Yeah,
specs, I'll call it, now you've got a single coherent model.
yeah.
All right. And, you know, if you want to look at a different way to do part of it, let's say you want to, you know, unplug this part and plug something back in, you know, and you do that, it's like, ooh, I got to take care of these two
Yeah,
dangling functions or interfaces, whatever you want to call it, you know, out here. But then you can ultimately, you know, you can actually run simulations on the system engineering models and see how they work. You know,
Yeah.
do they still perform to meet the use case that's also part of the system engineering model?
Yeah.
So it gives you a lot more freedom on what I'd call technology insertion when you've got a system
Yeah.
that you're maybe wanting to upgrade and you're looking at rolling that new technology in. That is one of the big value propositions of MBSE is sustainment and upgrade.
okay. All right, well, we've covered a lot. I feel smarter.
Well, I do too, Steve. I always enjoy talking to
Well,
you.
and model-based systems engineering is like, you need to get on board. That's why. Anyway, thank you for being with us.
It's my pleasure,
Dale
Steve.
Thomas, thank you. Go back and do eminent scholarship at UA.
I'll go back and pick my geek back up. Yeah.
And thank you for being with us. And remember,